Asgarli. Am I correct to pronounce? Okay, okay, thank you. Actually, thank you very much for inviting. For taking this invitation, and thank you very much for joining us, for participating in this workshop. So Shamil will give a talk on some properties of pseudopaleographs. The floor is yours.
Thank you. Thank you very much, Elena, for the invitation. Is this talk being recorded? Or?
Right, yeah. Can we?
Sure.
Okay, thank you.
Well, thanks again for the invitation. So today I'm going to talk about rigidity of maximum cliques in pseudopaleographs from unions of subatomic classes. And everything I will talk about is joint work with Chiho Yip. He also goes under the name of Kyle. So Kyle is here and he will give a talk after me. He's a PhD student at the University of British Columbia, and he's already kind of a resident expert in this topic. And he has more than 10 papers on subjects related to paleographs. So if there's any question that I'm unable to answer, please direct them to Kyle. He'll be able to answer it. So I'm going to start with very basics. So I'll start with the introduction to the graph that is the main player of all the series of talks today, which is the paleograph. And then after some preliminary discussion, I will talk about a generalization of paleographs. There are many different generalizations of paleographs, as you will see today, but one particular one I will talk about is pseudopaleographs, which is basically, those graphs that look like paleographs from spectral point of view. And then finally, I will state the main results that we have in the paper with Kyle. I won't be able to give proofs. Really, it will be mostly like a survey type thing. But we have several main results, so I will sketch and make sure that the statements are clear. So let's start with the paleograph. This is probably the most important definition in this subject. So suppose we have a prime power. Q is a prime power. For technical reasons, I will assume that Q is equal to 1 modulo 4 for the definition that will follow. As usual, FQ denotes the finite field of order Q. Then we can define the paleograph PQ of order Q as follows. So it's a graph, which means I have to tell you the vertices and the edges. Well, the vertices are simply the elements of the field. We write FQ plus here just to indicate that I'm looking at the additive abelian group structure of the finite field. But for all purposes, the vertices are simply elements of the finite field FQ. And I also have to tell the edges. Well, the edges are determined as follows. There's an edge between X and Y if X minus Y is a square element in FQ. And as we know, if you look at the non-zero elements in FQ, exactly half of them are squares and half of them are non-squares. So this is an interesting incidence relation among the vertices. So this is going to be a graph with the edge density 1/2. So everything that you want to know about squares in a finite field, in some sense, is encapsulated by the paleograph, because paleograph exactly encapsulates the condition of what it means for two vertices to differ by a square. And if you're familiar with the notion of a calligraph, which I'm sure everyone here is that you can write this in more compactly as follows. So in the language of calligraphs, paleograph PQ is calligraph where the underlying vertex set is the abelian group FQ plus, and the connection set, which is what determines the edges, is just the square elements in FQ, non-zero square elements in FQ. And in general, a Cayley graph construction works like this. So the first entry is an arbitrary abelian group, G, and the second entry is an arbitrary set S. And this is a graph where the vertices come from the group G, and edges are determined as follows. X and Y are incident, if and only if X minus Y lives in the connection set S. And as we will see in this talk, this is a very natural way of constructing interesting graphs. So Paley graphs are highly symmetrical and they enjoy many special properties. They appear everywhere, from combinatorics to finite geometry, Ramsey theory, and as we'll even see in this talk, some notions of analytic number theory. And if there's anything unclear in my talk, please feel free to interrupt and ask me questions. Just to show you how symmetrical they look, here is an example of a Paley graph. So this is the Paley graph P13. That means it has 13 vertices. So the vertex set can be labeled from 0 up to 13. And the label vertex labeled I represents the congruous class I modulo 13. And the edges are determined according to the definition. So for example, there's an edge between 11 and 2 because 11 minus 2 is 9, which is a square mod 13. And so, yeah, there's not much here other than showing you that these are highly regular graphs. And yeah, I guess I'm just illustrating also the notation being used freely. So there's really only one Paley graph for each order, and it's written PQ if it has order Q. The kind of questions we're going to be interested in this talk is about cliques in Paley graphs. So in particular, maximum cliques. So let's take a Paley graph. We'll call it X. X is a Paley graph of order Q. So this is PQ. We're interested in the clique number omega X. So clique number is denoted by omega X, and it's a standard notion from graph theory. It measures the size of the largest complete subgraph inside X. And this is a very hard problem in general. I'm not going to talk more about this. In fact, Kyle, in the talk right after me, will talk a lot about this problem. But this problem is notoriously difficult. I mean, essentially, we don't know the answer to this question. And if you think about this question, in down-to-earth terms, it's a very concrete question. It's not a question about graphs even. It's a question about squares in a finite fields. So what is the clique number measuring? It is measuring the largest size of a complete subgraph. In this particular case, what is it measuring? It's measuring the largest collection of elements in a finite field FQ, such that the pairwise differences are all squares. That is the equivalent way of stating this problem. And that problem is a difficult problem from sort of arithmetic point of view. Understanding when pairwise differences are squares. It's just a difficult problem. But there is one exception. There is one exception where we understand the clique number. And that is the case when the Paley graph has square order. So what that means is that we have a Paley graph X, which is PQ square of order Q square. So why is this a legitimate thing to consider? Well, Q is a prime power, and so Q square is also naturally a prime power. Because Q square is a prime power, we are allowed to consider the Paley graph of order Q square because there is a field of order Q squared. And so the vertices of this graph is just elements of this field. It's F sub Q squared. It's a finite field with exactly Q square many elements. Now, why is it so special to consider these graphs? Because these graphs admit a certain algebraic substructure. Namely, the finite field with Q square many elements naturally admits a subfield, FQ. And you can check, it's kind of an exercise, to check that every element of this subfield, FQ, seen inside a bigger field is a square. So as I mentioned earlier, if you look at a finite field, if you just look at that field and nowhere else, half of the elements are squares, half of them are non-squares. But here I'm saying something else. I'm saying if you take every element here, FQ, it actually becomes a square inside a bigger field. Every element of FQ becomes a square inside a bigger field, FQ square. But then by definition, it means that FQ appears as a clique inside FQ square because it consists of a bunch of elements where pairwise differences all are squares. This in particular shows that the clique number of the graph is at least Q because we found a clique of size Q. So the largest clique must have size at least Q. On the other hand, this is one result that we do know about Paley graphs of any order. This is called the trivial upper bound in the clique number, even though it's not so trivial. this result says that for any Paley graph of order Q, the clique number can be at most square root of Q. Okay, well, let's go ahead and apply this bound in the particular case that we have. Well, in this case, X is a Paley graph of order Q square. So if I just look at this inequality here and just plug it in Q square every time I see Q, then this side is going to become PQ square, and this side is going to become Q. So that means that a Paley graph of square order must have a clique number at most Q. And now we just combine this inequality with this inequality, and these inequalities are pointing in the opposite direction. So we get the clique number of PQ square. The clique number of the Paley graph of order Q square is exactly Q. And so this is just a very remarkable thing that we can exactly determine the clique number of a Paley graph of square order. But anything else, we basically have no idea how to do it. We have good upper bounds and lower bounds, but we don't have an answer. So we don't even know the answer when Q is a prime. So if you look at Paley graphs of prime order, and again, Kyle will talk about this in the next talk, but it's just a really difficult problem. But in this case, there's something interesting happening. And what is so special about Paley graphs of square order is that, again, they admit this sort of algebraic substructure. So, well, now that we know the clique number of a Paley graph of square order, it makes sense to ask about the actual classification of maximal cliques. So far we found one clique, namely FQ, but what about other cliques? What about other maximum cliques? We know they must have size Q by this result, but is FQ the only one? Well, here's a question that tries to answer this. So this was actually conjectured by Van Lint and McWilliams, that every maximum clique in the Paley graph of order Q square containing 0 and 1 is the subfield FQ. So the point is that for trivial reasons, the only maximum clique is not FQ, because you can always translate FQ. I mean, if FQ works, some other translative FQ also works. But if you fix 0 and 1, if you fix your clique to contain 0 and 1, Van Lint and McWilliams believed that the only possible clique with this additional hypothesis must be the subfield that we found. And if you don't want to impose the condition that the clique contains 0 and 1, you want to maybe write down the most general statement about maximum cliques in these graphs, you can state it as follows. So the conjecture by Van Lint and McWilliams is equivalent to the following statement, that every maximum clique of PQ square is an affine transformation of the subfield FQ. So once you have this statement, you can immediately get the original statement, because the only affine transformation that fixes 0 and 1 is the identity, and you're done. They can prove their own conjecture in the case when Q is prime, but it was not settled until Blockhouse's work. So Blockhouse proved their conjecture. So now this result is known, and it's often called Akademgorodok property of the Paley graph. I'm not going to talk much about why this is called the EKR property. Sergey might mention a little bit of that in his talk. But essentially, it's analog of a result from extremal combinatorics. OK. So here's a motivating question that drives the rest of this talk and rest of this project is, what makes the Paley graph so special? How much can we generalize some of these fundamental results about Paley graphs to general Paley graphs? And there's a lot of work that has been done on this, and I'm not going to be able to enumerate all of them. And the most natural one, in fact, I would say, is the generalized Paley graphs that, again, Kyle will talk about. So I don't want to say too much about it, but essentially, instead of saying like edges are determined by the condition that x minus y is a square, you say edges are determined by the condition that x minus y is a d power, where d can be any positive integer other than 2. It could be 3, 4. And for those generalized Paley graphs, it's also known, a similar result is also known, and that was proved by Szykli. But in this talk, we're going to discuss another big family of Paley graphs and hope to try to answer this question. And this question is so vague, it's not really possible to answer it. But somehow there's something so special about the way maximum cliques are classified in these graphs, and it is highly desirable to do so for other such regular graphs. So one last thing I'm going to talk about the intro before I move on to a definition of pseudopaleograph is a Pzero graph. And Pzero graph is something that Sergey will talk about. So I will just quickly define it. So this is one graph that looks very similar to paleograph. So how is this graph defined? So you start with an odd prime P, and you look at the case Q equals to P to the R, but you add this condition that R must be even. So again, this is just a prime power. So we can consider the finite field of order Q, and we're going to let G to be the primitive root of that field. Okay, so G by definition generates a cyclic group FQ star. And now we're going to consider this particular set. This set is going to consist of half of the elements, half of the non-zero elements of the field. And it's going to consist of exactly of the elements of the form G to the power of J, where J is 0 or 1 modulo 4. So we know that if you look at the primitive root and look at all the possible powers of the primitive root, you will get all the non-zero elements of the field. That is the definition of the primitive root. But here I'm not allowing the exponent to run over all possible integers. I'm forcing the exponent to run through those integers that are 0 or 1 modulo 4. And from this, we define the Pzero graph, and this graph is denoted by PQ star. It is the Paley graph on the additive abelian group FQ, and then with the connection set being MQ. So this is the connection set. So what that means, again, just to recap, it means the vertices are elements of the finite field FQ, and the edges are determined as follows. So two vertices X and Y are connected by an edge, if and only if X minus Y lives in this particular set. Now, this has a lot of resemblance to the Paley graph. Imagine just for a moment, I modified the definition slightly, and instead of saying G to the J where J is 0 or 1 modulo 4, I said it's G to the power of J where J is 0 or 2 modulo 4. In that case, I'm just getting the set of squares, and I recover the Paley graph. So here I'm not looking at even exponents, because that would be the case J equals to 0 and J equals to 2. I'm looking at this, like the first part of the interval, 0 and 1. So it's kind of this shifted connections that we're looking at. But again, it has the half edge density because these elements are about half the elements. And you get a very interesting graph. And these graphs were introduced by Pzero, and they're symmetric and self-complementary, just like the Paley graphs. So I'm not going to talk much about them, but in the literature, you may see them as P star graphs. That's how Pzero introduced them. But now, instead of calling P star graphs, we still use this notation, but we call them Pzero graphs. And I just want to mention one thing that we have recently extended with Kyle. We've extended the result, the blockhouse result for the Pzero graph. And this was a conjecture of Mullen, that the same conjecture, the only subfield, so only clique, maximal clique containing 0 and 1 must be the subfield. We prove this conjecture. I don't want to talk much about this because it's not the content of this talk. And I also wrote almost here because we have an assumption in the theorem. We don't prove it for all Q. We prove it for the case when the exponent is sufficiently large. The prime is sufficiently large with respect to the exponent. So there's some asymptotic, but we prove it. We almost prove it basically. So if you're interested, you can look at my paper with Kyle. It's called von Lint-McWilliams conjecture and maximum cliques and calligraphs for proof of this result. But now I'm going to talk about the actual contents for this project on rigidity of maximum cliques. And for that, I need to introduce the notion of a pseudopaleograph. So before we do that, we need to talk about strong irregular graphs. And I know this being a conference in algebraic graph theory, most people probably know this definition by heart. So I'm going to be a little bit brief, but if you have questions, feel free to interrupt and ask for clarification. So we all know what regular graphs are. Regular graphs are the ones where every vertex has the same degree. Strongly irregular graphs are refined versions of such graphs that keeps track of constancy of not just the vertex degree, but in fact the constancy of the common neighbors, the number of common neighbors. Let me explain this more precisely. So paleograph will be, in particular, an example of a strongly irregular graph. But let me tell you the definition. So if Y is a k-regular graph with n vertices, such that any two adjacent vertices have lambda common neighbors, and any two non-adjacent vertices have mu common neighbors, then we say Y is a strongly irregular graph with these parameters n, k, lambda, mu. So if I was just looking at regular graphs, then I would just have this first sentence and I'd be done with it. A regular graph is a graph where every vertex have k neighbors. But here, and those are exactly the first two parameters here, n and k. So n is always going to be, the first entry is always going to be the number of vertices, and k is always going to be the number of neighbors of any given vertex. But in this definition, I have two additional constants. They're lambda and mu. And lambda is characterized by any two adjacent vertices having lambda common neighbors. And mu is the number where every two non-adjacent vertices have in common. So every two non-adjacent vertices have mu common neighbors. And these graphs are actually, as you can see from the definition, they're very symmetric. And as far as I know, this is still an open problem to classify all strongly irregular graphs. So if I give you these four numbers, n, k, lambda, mu, just randomly, satisfying the obvious and necessary constraints, can you find a strongly irregular graph with these parameters? That is, as far as I know, is a very difficult problem. And people have classified certain strongly irregular graphs with these parameters. So Paley graph is an example of a strongly irregular graph, and these are the parameters it has. So again, we assume that q is equal to 1 modulo 4. Then the Paley graph is a strongly irregular graph with these parameters, q minus 1 over 2, q minus 5 over 4, and q minus 1 over 4. And then, in fact, the eigenvalues of the adjacency matrix of the Paley graph can also be determined exactly. There are three of them. There is the principal eigenvalue, which is q minus 1 over 2, and this occurs with multiplicity 1. And then there's these two conjugate eigenvalues, and they occur with multiplicity, high multiplicity, multiplicity q minus 1 over 2. So this is actually a general fact that if you have a strongly irregular graph, any strongly irregular graph, actually you can determine the eigenvalues of the adjacency matrix. In fact, there's only 3 distinct eigenvalues of any strongly irregular graph. I mean, this is a fact that is a standard fact, but it's completely not obvious. And not just that. In fact, the eigenvalues of a strongly irregular graph can be determined exactly by precise formulas using these parameters n, k, lambda, mu. And if you look at these formulas and plug them in the case of a Paley graph, you will get these numbers. So now we're finally on the slide that has the definition of a pseudo-paleograph. So what is a pseudo-paleograph? Well, here is the important definition. So pseudo-paleograph is a strongly irregular graph with the same parameters, namely n, k, lambda, mu, as the Paley graph, pq, for some q. So because the parameters of a strongly irregular graph determine completely the eigenvalues of the adjacency matrix, you can define pseudo-paleographs as follows also, if you like. An equivalent way of defining pseudo-paleographs is as follows. Pseudo-paleographs are precisely those strongly irregular graphs that share the same spectrum with the paleographs. And by spectrum, I mean they share the same eigenvalues with the same multiplicities as the paleograph. So pseudo-paleographs are indistinguishable from paleographs from the point of view of spectral graph theory. So if only what you know is the eigenvalues of the adjacency matrix, then the pseudo-paleographs and paleographs are more or less the same. I mean, they are literally the same. So this is a very natural definition.
Can I ask one question here? Can you clarify that you define pseudo-paleograph only for the Q prime power?
Yes.
Because I see.
Right.
So
yeah,
for
that's
example,
actually a good question. So that's actually a very good question, because you can define pseudo-paleographs more generally, you could just say they have the same parameters as the Paley graph, like this, but Q isn't allowed to be not necessarily
non-prime power.
Yeah, and that would in fact be a more general definition. Now,
But
whether
do you
there are
restrict
examples of that, I'm not sure. But yeah, that's what's that?
Yeah, do you restrict yourself to the case where Q is a prime power?
I believe so. I believe we do.
Yeah.
I just
want
to.
Yeah.
No, but that's actually Thanks for the clarification. But that is a good question. So yeah, thank you very much, Akihiro. So as Akihiro says, this definition, in fact, is not as general as it should be because Q doesn't need to be a prime power. And it would be interesting to come up with those examples, interesting examples of them. So I should mention something, though, that all the examples we can come up with, I mean, at least I know, involve the finite field FQ as its vertex set. So therefore, it has to be a prime power from the constructions that we have. So I don't know a construction off the top of my head where it is the case. So I would love to see an example, which I believe exists, of a strongly regular graph with the same parameters of the Paley graph where Q is not a prime power, because such a graph would have to arise from non-algebraic. It have to arise from something other than a finite field of order Q. And it'd be good to see an example of that. Very good question. So pseudopaleographs are those graphs that share the same spectrum as Paley graphs. So there are two natural questions that arise, two very natural questions. Are there systematic constructions of pseudopaleographs other than the paleographs, right? So we have this definition, but I mean, every time you have a definition, you have to ask yourself, are we defining something trivial? Because what if the only pseudopaleographs are just the paleographs themselves? So that would mean that this is a bad definition. So we need to figure out how to get new graphs that look like paleographs from the spectral graph theory point of view. And then of course, the most natural question that arises after that, in view of the discussions that we've had so far in this talk, is what can we say about maximum cliques in such graphs? So any kind of general statements that you can prove about maximum cliques in pseudopaleographs will apply in particular to paleographs. So you may hope to generalize results like, Blockhouse's theorem or other results. So, any theorem that you see about paleographs, you can immediately ask about pseudopaleographs. And the ones that I will consider in this talk is about maximum cliques in such graphs. And already here, we're going to see something interesting. So I won't spoil it yet, but we'll see. So I'm going to go ahead and talk about the first bullet point. So are there systematic constructions of pseudopaleographs other than the paleographs? So I will try to answer this. Well, here is a construction involving the notion of cyclotomy. So this is a concept that's purely about field theory and like number theory. In fact, the graphs don't appear in this slide. So in this definition, we're going to fix a ground field FQ and a choice of a primitive root G of this finite field FQ. And here's a definition of a cyclotomic class. So let's start with any number, capital N. This number is fixed from the beginning. And this is going to be any number that divides Q minus 1. Because N divides Q minus 1, that means that we can find the subgroup C0 of FQ star with index N. This is because FQ star is a cyclic group. So if you have a cyclic group of certain order, any divisor of it, there's a subgroup of of that index. In fact, there is a unique subgroup of index N. So C0 is going to be a subgroup of index N. And then, well, if you have a subgroup of index N, it means it has N cosets. And what are the N cosets? There are C0, C1 up to Cn minus 1, where Cj is simply G to the power of JC0. So that's it. That's all. So these are called cyclotomic classes. So C0, C1 up to Cn minus 1 are called nth cyclotomic classes of FQ. And there is a technical definition here, which is very important actually, is that sometimes we're in the special case where minus 1 is a power of P modulo n. What that means is that p to the t is equal to -1 modulo n. And this condition is so special that it has a name. It's called the semi-primitive case. So in this particular case, when -1 is the power of p, we will say that these cyclotomic classes are semi-primitive. So let's look at a simple example. When n is equal to 2, then C0 is going to be the subgroup of index 2, and we can write it down. C0 is simply the set of all squares, set of all non-zero squares in the field. And then, well, what's going to be the coset? Well, there's only one other coset, which is C1, and that's going to be G times G squared. And these are going to be the two cyclotomic classes in this case. Okay, so now we are going to talk about the main definition, main graphs that we're going to consider. So remember here early on, I told you, I asked you, are there systematic constructions of pseudo-paleographs other than the paleographs? And this is what I'm going to answer. After defining cyclotomy, I'm going to define this notion of a semi-primitive pseudo-paleograph. There's actually, if maybe a couple of words we're missing here, it should really be semi-primitive pseudo-paleograph coming from a union of cyclotomic classes. That's a more precise way of referring to this construction. Okay, so how do we define these graphs? So suppose Q is a prime power, and D is a positive integer, such that 2D divides Q minus 1. Okay, so we're going to consider 2D cyclotomic classes, right? For me to talk about 2D cyclotomic classes, I need this divisibility condition. Because remember, here we had this condition, n divides Q minus 1. That's exactly what I'm imposing here. So Q is a prime power, D is a positive integer, and 2D divides Q minus 1. That means we can talk about 2D cyclotomic classes. And I'm going to let I to be some subset of size D inside the number 0 up to 2D minus 1. So what I'm really doing here is I know that there are 2D distinct 2D cyclotomic classes, and I'm only taking D of them. That's what I'm doing. So let's let C0, C1, all the way until C2D minus 1 to be all the 2D cyclotomic classes of FQ. And this I is kind of parameterizes some D indices. So about half the indices, right? So what is the graph that we're going to consider? We're going to call it PPQ2DI. And we're going to explain what this means. Well, you can guess what PP means here. It means pseudo-Paley. So pseudo-paleograph, so it's going to have 3 parameters. Q will tell us the vertex set, FQ. 2D is going to tell us which kind of cyclotomic classes we're considering. It's the 2D cyclotomic classes. And I is going to be exactly this index set that parameterizes which indices I'm picking. I'm picking exactly half of the indices. And actually, that's why I need 2D to be even. And I'm picking half the indices, and that parameterizes that. And this graph is going to be defined as this following Paley graph. So it's the Paley graph. It's the following Paley graph, where the vertex set is just FQ, and the connection set is D, where D is a union of cyclotomic classes indexed by my set I. So this is why the name of this talk is cyclotomic rigidity in graphs coming from a union of cyclotomic classes, because I'm taking union of cyclotomic classes. Well, which union am I taking? I'm taking any union consisting of D cyclotomic classes out of 2D possible cyclotomic classes. So this is kind of reflecting again how in the case of Paley graph and the Pzero graph, we were taking sort of half density objects. The connection set we always had half density. That's exactly what's happening here. So yeah, again, so the vertices are just elements of the finite field FQ, and the edges are determined as follows. X and Y are adjacent if and only if X minus Y lives in this set D. And in the case that -1 is a power of P modulo 2D, that means we're in the semi-primitive case. And in this case, we say that X is a semi-primitive pseudopaleograph. So a semi-primitive pseudopaleograph coming from a union of cyclotomic classes is this construction. It's a calligraph like this, where D is obtained from some D. So capital D is obtained by taking some little d many cyclotomic classes. So I'm just going to pause here and make sure this definition is clear, because there is quite a bit of symbols floating around in this slide. Okay. So important thing here is that the notation PPQ2DI, and these are the relevant parameters, Q, 2D, and I, which is the index set, actually. So when you have a definition this involved at first sight, you might be skeptical about usefulness of it. Does it really encapsulate anything? And in the next slide, I'll explain why is it significant. But before that, I forgot that I do have one extra line. So in the case that we're considering when X is a semi-primitive pseudopaleograph, we're going to write Q to be P to the 2RT, where T is the smallest integer satisfying P to the T equals to -1 modulo 2D, and R is going to be any integer. So for this particular case, this is the case where -1 is a power of P. This is the semi-primitive case. You can show that using these congruence conditions that Q can be written in the form P to the power of 2RT. Right. So this is just notation. So if you see Q equals to P to the 2RT, I will implicitly assume that T is that smallest exponent which satisfies the semi-primitive condition. Okay. So as I mentioned, all of this, the constructions are kind of number theoretic or field theoretic. So why is it significant to consider semi-primitive classes? But this is because, well, first we have a lemma by Brouwer, Wilson, and Chiang that says that there is a connection. There's a connection between being a union of a semi-primitive cyclotomic class and being strongly regular. So what they showed is that any calligraph on this vertex set FQ plus, where the connection set is a union of semi-primitive cyclotomic classes, this is strongly regular. So you can get many classes of strongly regular graphs using this construction. And all of these graphs will have necessarily a prime power cardinality. Of course, these are not the only way to get strongly regular graphs. It's just one general construction of strongly regular graphs. And as a corollary, so this doesn't say anything about these graphs being pseudo-Paley. Pseudo-Paley graph is a very special type of strongly regular graph. It's namely the one which shares the same eigenvalues as the Paley graph. And you can use their work and some other work to show that when we're in this case that I considered, where we have sort of half of the cyclotomic classes under consideration, and Q is equal to P to the 2RT, where T is the smallest integer satisfying this condition. So in the condition that I described earlier in the previous slide, you actually do get a pseudo-paleograph. So this already tells you the graph is strongly regular. What you have to do is you have to check that with these parameters, you actually get a pseudo-paleograph. So you also have to check that the eigenvalues match. And here it's essential that we use this construction where we use half of the cyclotomic classes, because the Paley graph has half edge density. So that's why it's kind of important here that we're picking exactly half of the cyclotomic classes to consider. And you can check that, this is a pseudopaleograph. And again, the notation PP stands for pseudo-Paley. So I'm not going to say much about this corollary, except that this kind of answers one of the motivating questions. This answers that question I raised about systematic constructions of pseudopaleographs. And this is it. This is one cyclotomic, this is one systematic sort of generation of pseudopaleographs. Okay, so to explain that this concept is useful, I will show you that by specializing the choice of the set I, we will recover several important families of caligraphs. So if you look at the case PPQ2 and 0, the set consisting of 0, you can show that you get the paleograph. Because here you're just picking the 0 coset, the 0 cyclotomic class in the case of squares. That means your connection set is simply a set of squares. And so you immediately get paleograph as a very specific example of our construction. Similarly, if you look at 2D being 4, and I want my connection to set pick up exponents with g to the j, where j is 0 or 1 modulo 4, I get exactly the Pzero graph. So Pzero graph is kind of obtained as a special example of our construction. And then you can also check that you get a paleograph with a different connection set, with a different index set. Here you're just taking all the even numbers, and you still get the paleograph. So it is possible to have different index sets and different Ds where you get isomorphic graphs. Not just isomorphic graphs, but literally the same graph. So you can check that if you look at the odd numbers, you get the complement of paleograph, and complement of paleograph is known to be isomorphic to paleograph. And you can also get something called the generalized Pzero graph this way. Instead of taking 0 and 1, here instead of 4, you can take any 2D and just look at the first D entries. You get this concept of generalized Pzero graph. And there's also something called Pzero type graph that Sergey may talk about. You also get that as a specific example. So now I don't have much time, so let me quickly go through the main results. So the first main result is a non-isomorphism result that shows that you really get something new. You don't get duplicates of paleographs most of the time. So to talk about that, we need to talk about minimal representation, because sometimes two different expressions may represent the same graph. We want to take the minimal representation to get rid of redundancies. And the minimal representation is defined as follows. We say that pseudopaleograph is a minimal representation if there is no D prime that divides D, no divisor of it, no proper divisor, and no index set inside a smaller set, such that X is equal to a smaller version of this graph. So basically, you just take the smallest possible version of this graph, and that's going to be a minimal representation. And what we show, one of the results we show is that if you take any pseudopaleograph, there's no assumption of semi-primitivity here. Any pseudopaleograph coming from this construction with some condition, the Q is not one of these 4 exceptional numbers, then what we've shown is that if D is equal to 1, then X is the paleograph. It's isomorphic to the paleograph. If D is 2, then it's isomorphic to the Pzero graph. And if D is at least 3, then X is not isomorphic to PQ or PQ star. So this is saying that this is completely new graphs that we get from this way. And this in particular confirms the conjecture by Mullen, because Mullen conjectured that generalized Pzero graphs are not isomorphic to paleograph or the Pzero graph. This follows from it, because a generalized Pzero graph is an example of our construction, and that's why from part 3 of this theorem it follows that it's not isomorphic to the paleograph or the Pzero graph. To state the main result, the really main result is the rigidity of maximum cliques in pseudopaleographs. I need to talk about rigidity of maximum cliques in a paleograph. So this is something that's well known, which is that, or maybe not well known, but maybe not hard to establish, is that if you take the paleograph, so this description is just a description of the paleograph, so we can actually just ignore this. If you just take the paleograph, PQ, then if you take any maximum clique in X that contains 0, then you can show that the contribution from each cyclotomic class, C0, C2, all the way until C2D minus 2, is exactly the same. It's root Q minus 1 over D, because maximum clique containing 0 must have size root Q, right? That's by Blockhaus theorem. And so this is how many cyclotomic classes are there. There are D cyclotomic classes, and we're saying that the elements of the maximum cliques are like equidistributed along the cyclotomic classes. And this is a statement about paleograph, and you can check that. I don't have much time to go through the proof, unfortunately. I assume I have 5 minutes. I assume it's 50 minutes talk, so I don't have much time to go through this proof, but if you're interested, you can check my slides later about how you prove that. And it's not very hard to prove because we know what paleograph looks like concretely. The connection set is rather easy to describe. So you can just do a computation to see that in the case when the clique is F root Q, this is true, and the same argument works for any maximum clique that has the form A times F root Q. And by Blockhaus theorem, every maximum clique that contains 0 has to look like this. So we really have exhausted all possibilities. So this is a computation that you can check in the specific case of a paleograph. And our main result says that this equal contribution result along cyclotomic classes extends to all pseudopaleographs coming from semi-primitive cyclotomic classes. So our main result extends this theorem, extend this property, and this is the theorem. So if you start with this construction of PPQ2DI, and if this is any semi-primitive pseudopaleograph, where, again, the vertex set is FQ, where Q is P to the 2RT, and R is even, and I is any index set that has half of the cyclotomic classes. Well, first of all, we show that the clique number is bounded by root Q, and we also show that, so this is like the trivial upper bound on the clique number, and we also show that if the clique number is root Q, then if you take any maximum clique in X such that it contains 0, then the intersection of A with each of these cyclotomic classes that you chose is equal. So this is the equal contribution result for pseudopaleographs. And you can see that it exactly generalizes the result for paleographs. And the key tool in the proof, which I'm not going to obviously prove in so little time I have, but is a result that you might find interesting. It's actually a Fourier analytic characterization of maximal cliques. And it states the following, that if you take any pseudopaleograph PPQ2DI, of course, semi-primitive assumption is needed, then if you take any clique in X, then it's got size at most root Q. But moreover, if it has size root Q, then certain Fourier coefficients vanish. So if and only if certain Fourier coefficients vanish, and namely this one. So the Fourier coefficient, this expression vanishes for every C in this set. And this is minus MJ. This is not a typo. It really should be minus MJ here. So again, so this is a technical result, but you might find interesting. And this idea is actually due to Kyle himself from an earlier paper of his. This is sort of slightly generalization of that argument. And the idea is to use Fourier analytic argument over finite fields and explicitly evaluate Gauss sums and certain character sums. And that's where we use the semi-primitive assumption. It turns out that you need semi-primitive to evaluate these Gauss sums rather explicitly. The natural question is, do we have EKR property for semi-primitive pseudopaleographs? Namely, do we have that nice classification like Blockhaus result? And it turns out that it's not necessarily the case. So first of all, we don't have a subfield construction. So we can show that in general, if I is not the index set that corresponds to the paleograph, then in fact the subfield is never a clique. So this is very different from the paleograph case where there was an explicit subfield that formed a clique. This is not the case. And we made a conjecture which says that even if F root Q is not a clique, every maximum clique will be an FPT affine subspace. So this is a main conjecture in our paper, and we haven't really been able to prove it. But we made some sort of strides towards proving this conjecture. So this result can be seen, this conjecture can be seen as a generalization of Akademgorodok theorem, and also something known as Hvatal's theorem for set systems in the context of pseudopaleographs. So it's 1:50, and I assume my time is up now. I had a few extra slides left, but I didn't get there, and that's okay. So thank you very much.
Well,
Yeah.
I think that you can continue just during 5 minutes, and then
okay.
there will be questions. Are you fine with this?
Sure, I'm fine.
Okay,
I'm fine.
thank you.
Okay, thanks so much. Yeah, I would love to continue for 5 minutes. Okay, so the next result, I only have like 2 slides left, I believe. So the next result is that this shows that the EKR theorem that I showed you in the beginning, that Blockhaus proved, is very false for the case of pseudopaleographs in general. So I would say this is kind of a nice result because it just shows you how special the paleograph is. So if you take any semi-primitive pseudopaleograph, where Q is P to the 2RT with R even, then you suppose that the index set contains 0, but I is not equal to the index set coming from the paleograph, then we have the following result. If the clique number is root Q, then there are at least 2 maximum cliques that contain 0 and 1. So notice how this result is in complete contrast with Blockhaus theorem, because Blockhaus theorem said that there is a unique maximum clique that contains 0 and 1, namely the subfield FQ, but here we show that's not the case. There's at least 2. And we've shown something more. We have shown that in the particular case, when Q is equal to P to the 4T, then we've shown that such a semi-primitive pseudopaleograph has even number of cliques, of course, possible 0, of size root Q, that are subspaces defined over FP to the T containing 1. And furthermore, so every time you have something like even number of cliques, you may ask yourself whether they're paired up. And we have shown that they are paired up in the most natural way. We have shown that in this case, these maximum cliques actually come in pairs that are interchanged by this Galois conjugation, x goes to x to the root Q. And the last slide is about conditional improvements on the trivial upper bound. As I mentioned earlier, the clique number problem is extremely notoriously difficult. And here we have been able to make some progress, but the progress assumes the main conjecture I told you earlier. And the main conjecture says that maximum cliques have subspace structures. So assuming this result, assuming that maximum cliques have a subspace structure, notice I'm not saying a subfield structure, I'm saying only a subspace structure. We can show the following result, that for any semi-primitive pseudopaleograph, as long as it avoids the case of the paleograph or the complement of the paleograph, we can show that we can improve the trivial upper bound by 1. So instead of saying omega of x is at most root Q, we can prove that omega of x is at most root Q minus 1, assuming that the prime P is sufficiently large. And there's some technical assumption, P to the T has to be large enough. And finally, we also show a result on the clique number of generalized paleographs, and also, generalized PCA graphs, and also PCA graph of order P to the 4. We show that you can improve the trivial upper bound on the clique numbers, assuming the main conjecture. Yeah, it's kind of in the same spirit as this one, but it's kind of a more precise result. Okay, I think that's it for my talk. So thank you very much. Thanks for letting me go over time also a little bit. And here's some references that I mentioned during the talk.
I see. Okay, thank you very much for this very interesting talk. Are there questions to Shamil?
Thank you. There's a hand, Chris.
Okay.
I had a question.
Yeah, sure, please, Chris, yeah.
Yeah, thank you. That was a really interesting talk. I was wondering, I had come across a paper a few years ago by Klein, Krieger, and Wolder, where they were looking at Paley graphs with Paley type parameters. They were trying to classify self-complementary and non-self-complementary examples. This construction that you gave reminded me a little of that. And I was wondering if that's more general or less general than this.
Maybe I'll like type this down. If you could just tell me the name of the authors.
Yeah, it's Misha Klein, Nimrod Krieger, and Andrew Wolder.
Okay. Yeah, I'll have to look that up. So I can tell you, I don't actually know at the top of my head that paper that you are referring to, but they were about self-complementary strong regular graphs. Is that what you said?
Yeah, they were trying to find more examples of self-complementary. They ended up using the fact that you can take any fusion of two-dimensional plane, essentially, that you had an amorphic association scheme, and they were looking for more examples of self-complementary.
And
graphs.
were they like using cyclotomy or something?
They were using Polya theory of counting. It was really interesting.
I see. Cool. I actually, yeah, I'm not aware of this paper, but I do know that, yeah, searching for strongly regular graphs with certain parameters is like a big problem, it seems like, in this field. Although, and I think this result is quite influential for that, the result by Brower, Wilson, and Xiang, and I think other people have done kind of similar thing, looking at new strongly regular graphs coming from these constructions. But we were considering just making sure that the graphs we get are not just strongly regular, but they're pseudo-Paley. And when we add that condition, we got this construction. But it's not to say this is the only way of constructing pseudo-Paley graphs, period. So there could be other constructions we are not aware of. And the one last thing I wanted to mention, you already know this potentially, this first thing about Pzero graph. So since you asked about this, since you mentioned self-complementary or strongly regular, like Pzero studied these graphs because these graphs are the only graphs other than the Paley graphs that are self-complementary and symmetric.
Symmetric, yeah, that's the actual.
And then other than, there's also one exceptional graph of order 23 square. But other than that, it's the Paley graphs, Pzero graphs. So those are the self-complementary symmetric. So kind of a lot of conditions. But if you just ask strongly regular and symmetric, I think it's very hard. Yeah, we don't really know classification.
I was also going to mention, just because I was sort of interested when you're talking about non-prime powers, I just looked up there's a graph of order 45 due to Mahon that has the 45, 22.
Okay, awesome. Due to Mahon, you said?
Maton, yeah, Mathon. It's in
great.
the standard. If you just look up the list of strongly regular.
Thank you so much. Thank you, Chris. I appreciate that. That answers Akihira's question. Yeah. Okay. Great. So that doesn't come from finite field. It comes from something else. Cool. Thanks so much. Any other questions in the next 2 minutes?
Where does the graph of order 23 squared come from?
Oh, yeah. Unfortunately, I don't know. I should know, but I don't know. It's so the classification of self-complementary and symmetric graphs uses group theory. And in the study of it comes from the study of rank 3 affine groups. And there in that classification, there is a exceptional group of that order. So I guess you would have to trace it back there. But I unfortunately, I don't have much knowledge of where that exceptional graph of order 23 square comes from. But if anybody is knowledgeable enough, please let me know.
Okay, thanks.
Sorry, I wasn't able to answer, but yeah, I will look that up though. I will try to learn it, and maybe we can. I'm not sure if we can draw it. I mean, 23 square is not too big, so it might be possible to draw it. Let's see.
Okay.
Rather you than me.
Okay. Well, I'm sure that there are many other questions to the speaker because the topic is quite interesting for the audience. but I think it is time to stop asking, Shamil. And if you would like to have any other answers on your questions, please just contact to Shamil. I'm sure that he will be pretty
I would be very happy.
to have these
everyone.
answers and questions. So thank you. Very nice talk. Yeah.
Thank you so much, Yelena. I appreciate it.